All right. So we are now into the final stage of the course. In the last class, we looked at this two-stage op amp. There were two things which we have to add to this op amp. Actually, three things, out of which two I will add, and then one I will not bother about right now. Okay. First, just to recap very quickly what's happening here in this two-stage op amp. What do you see? You see that you have the first stage, which is your differential input stage, correct? That's your differential stage. After that, what do you have? What's the next stage that you see? What is this stage? It's a common what amplifier? Common source. Okay, this you should be able to do. All right. Now, what is the output of the common source amplifier? Is it high or low impedance? It is high, right? Because in the ideal case, it will only be the resistor R0 of the op amp of the transistor, right? So, for an ideal op amp, what do you want? You want low output impedance. So, what can you do to this in order to get low input impedance? Exactly, you just buffer it. So, what kind of buffer should you put? Common drain, right? So, I have this common source stage, and then I have to have a common drain stage, which I did not add, but it really does not trouble any of the analysis we have done so far. Okay, so how will that look? Well, again, you can do it with an NMOS or a PMOS, but typically it is done with an NMOS in this particular configuration. If your first stage were an NMOS stage, right, and then the second stage is a PMOS stage, then the biasing and all of that seems to be that this stage becomes this stage again becomes an NMOS stage. Okay, and then again you have some kind of current source. So instead of having that current source here, we can have that. And what should I have on top? Nothing, right? And where should I take my output? Here. Okay. So this becomes your common drain amplifier, which acts as a buffer. Okay. So this improves your output impedance, and so, right? So this is about 75% of the story of the op amp. What happens is that if you look at any op amp circuit, this is followed up with a power amplifier stage. We have not discussed power amplifiers in this course, so we will let it be. Okay. So you just keep in mind that there is another stage that is cascaded to this stage, which is a power amplifier, which basically allows you to drive a very heavy load. Okay. So don't worry about what goes into the power amplifier right now. I am sure that it will be done in the next course. Okay. There are two other things. So those are the 2 points which I wanted to mention. There is one other point which has to be mentioned, and that is apt to mention right now. When we bias this circuit, we said that I naught is flowing through this arm. Hence, I naught, DC current I naught is flowing here, right? And then here you have I naught by 2. Okay, I should not say DC, let me say bias, because your op amp works for DC also. So you have a bias of I naught by 2 flowing here, and similarly you have an I naught by 2 flowing here. Okay. So what do you think should be the current flowing through M5? Right? You can actually make any current flow, but it is common to get I naught by 2 also to flow here. The reason being that you are taking, no, there is no mirror here, right? There is no mirror here, but what you are doing is you are taking the output from this stage and giving it as the input to this stage, and you want to ensure that whatever bias value is set up by this stage is identical to the bias for the next stage. And if you go through the details, it will work. It will turn out that if you have I naught by 2 here, you will need I naught by 2 there also. You can go and work out basically you work out what is the VSG for this transistor, and you want to ensure that you have the same VSG for this transistor, and that can easily be ensured if you have I naught by 2 and I naught by 2 flowing here if the transistors are identical. Okay. So, there is one small issue that we have to take care of. You have I naught by 2 here, which means this current is I naught by 2, right. So, you have an I naught here, correct. This M0 current mirror allows I naught to flow, but M6 should only allow I naught by 2 to flow. So, what can you do? Sorry? No need, no, don't look at deviation, you want it to be very precise. So, you remember there is a W by L ratio, correct. So, you can have a situation such that this is actually 2x, this is 2x, and then this is 1x. By 2x and 1x I mean that it is this 2x means the W by L ratio. Okay. So, this is 2 times something, this is also 2 times the same thing, and this is 1 times that. And just to keep in mind that when you say 2 times something, you are not really going to make W by L twice on the IC. What you will do is you will take 2 transistors and put them in parallel, so that if there is, you want to minimize any mismatches, right. So, exactly making another W which is twice the original W is hard, but making 2 transistors is going to be simple. So, this will actually look, if you go in and see it, you will see that it is 1 transistor, and then you will have another transistor, correct, and they are connected in parallel, which means that like that. So, this one will be that. Okay. Yeah. For right now we are not where. Yeah. R0. So, in current mirrors you have to consider R0, you have to consider noise and all of those things. You can also look at what happens if there is a small delta in the W by L. All of those things are higher order effects. It is not to be done in this course. Okay, it will be taken up later. All right. So, this is our 2-stage op amp. Okay, maybe 2 stage for amplification, and then some 1 more stage or 2 more stages for signal conditioning. 1 stage is the buffering stage, and then they have some power amplifier stage. All right. Is that okay? Okay. Okay. Now, the next point that I wanted to just discuss with you was the design of this capacitor, compensation capacitor CC. We have done this before, but I thought I will just do it again such that it is clear for all of you. Okay. So, let us just draw the op amp circuit again. Okay, the incremental circuit. Incremental circuit for the op amp looks like, I have a plus minus VD, then what do I have? I have 1 current source, have 1 resistor, then all of this has a common this thing. I have another current source, another resistor. Okay, what were the things? This was going up or down, this particular down, right? That was down, that was also down. So, this was GM what? GM what? GM 1, 2, 3, 4, 5. Go and see your notes. This is GM 3 times VD, correct? No, GM 1. This is GM 1 times VD, and this is R3. This is GM 5 times V01, and this is R6. Okay. Now, I also looked at 2 capacitors, right? Those 2 parasitic capacitors, and can anyone tell me why I took those 2 capacitors? Why did I take this C1 and C2 and CL over here as the dominant capacitors to look at, the dominant parasitic capacitors? You look at this stage, look at the first stage, right? It is going to drive the second stage, and at the input of the second stage, this is a common source amplifier, right? So, at this input you will have the CGS corresponding to this amplifier plus the Miller capacitance of this amplifier itself. That will be the dominant capacitance, and that is going to be this. That is why I put this C1 here. Similarly, if you take this stage, right, it is going to drive the next stage, and that is this. Okay. That is why I have taken just these two capacitors to do the analysis. All right. So, those two capacitors we'll put them here. I will call that as C1, and just for fun I am going to call this as C2. Okay. CL is your C2. All right. And what more and let me take some numbers so that it is clear. Let me take GM1 as 100 microsiemens. Let R3 be 1 mega ohm. Let this be 1 picofarad, and again similarly this be 100 microsiemens, 1 mega ohm and 1 picofarad. Okay. Can you tell me what is your transfer function for this whole thing? We worked it out that day. A of S was A naught divided by 1 by S by P1 into 1 by S by P2, correct? And what were P1 and P2? P1 was 1 by R3C1, P2 was 1 by R6C2. Okay. Now, in this particular case, when I take R3C1 and R6C2 values all identical, what will this become? I get P1 equal to P2 equal to how much for these set of values? 10 power 6 radians per second. Is that right? And what is your A naught? Your DC gain for this particular system? What's the DC gain of the first stage? GM1 R3. So that's 100 into 1 mega ohm. That will be 10 power. That will be 100, right? 100 into 100. That will be 10 power 4. All right. Okay. Now, can you tell me what is the so let me now take a situation like this. So this whole thing is your amplifier, right? So that is your amplifier, and let me connect it in a feedback path such that, so this is your K minus 1 times R, and this is R. Let me take K is equal to 10. Okay. So this amplifier is that amplifier, right? So this is your A of S. All right. Now, what can you calculate with all of this? Even I forgot. What should you calculate? Okay. Calculate your damping factor. What's the formula for damping factor? What kind of system is this? First order, second order? First order? I have not drawn the compensation capacitor yet, right? So this is without compensation. Right? What is your zeta? Do people remember this result? Okay. P1 by P2 plus root of P2 by P1. Okay. Then what was this guy? A naught by K or K by A naught? K by A naught. Right? You saw that for large values of A naught, the zeta was actually bad. Okay. So can you put in these numbers and tell me what is the value of zeta? So this gives you a damping factor zeta of 0.03. Is this a high value or a low value? This is a very low value. So what will happen because of this low damping factor? Your system will be stable, but it will oscillate like crazy, right? So you don't want this. So what do you want? You want zeta to be 1. Okay. So how do you make zeta equal to 1? So with the same circuit, I am still not going towards compensation, but I want to make zeta equal to 1. So what can I do? Assume that I am going to add a capacitor here. Okay, let me say I add a capacitor Cc like this, or yesterday I had called it C alpha. Okay, this capacitor, let me call that C alpha. So if I add a C alpha like this, right, and you want a zeta equal to 1, what can you do? How do you calculate it? So when zeta is equal to 1, okay, we calculated what P1 and P2 should be. There is a relationship between P1 and P2, and what is that? P2 must be equal to 4 times what? 4 times the unity loop gain frequency, which is A0 by K times P1, right? This is what we had already calculated. All right. Now if I add a C alpha like this, does it alter my P2? No, right? It is only changing P1. Okay. So now can you go back and calculate? So your P2 in this case, because it is unaltered, P2 is 10 power 6 radians per second. Okay, is 4 into what is A0 by K? 10,000 divided by 10 into P1. So can you tell me what P1 is? So P1 is 250 radians per second. Okay, and correspondingly, can you calculate what my C alpha should be? What is C alpha? So your P1 is equal to 1 by R3 into C1 plus C alpha. Now you note that your P1 was at 10 power 6 and your original P1 was at 10 power 6. This is your P1 prime, which is at 250. So which means C alpha is much greater than C1. So this is approximately nothing but 1 by R3 C alpha. Okay. So can you tell me what C alpha is? Tell me. 4 nanofarad or 40 nanofarad? Check. 4 nanofarad. Okay. So C alpha is 4 nanofarad. So you see what's happening. I have my capacitors of order 1 picofarad, and I want you to put a capacitor which is 1000 times the value of capacitors there in order to compensate this. Okay. So can we draw the Bode plot for this particular system? First with compensation, then without compensation. This is just an exercise for all of you. We are not doing anything new today, right? This is the typical kind of stuff that we can test you on. Okay. So for the magnitude, if I want to first draw it without any without compensation, how will it look? Let me say that is up to here, and then it should drop off at, so this is 10 power 6. Okay, and what should it drop off at? 20? No, you have 2 poles. The system without compensation, both are identical, right? So it's at 40, right? So it falls off at 40. Okay, and what am I plotting here? Let me plot the loop gain. Okay, I am plotting loop gain L of S. This is modulus of that. All right. So this value is going to be A0 by K, and A0 by K is 1000. Okay. So can you calculate what this frequency is? Approximately what should it be? This is falling off at minus 40 dB per decade. If I call this as omega 1 corresponding to P1, what should this be? No, this should be square root of A0 by K into omega 1, right? Because this is a 40 dB per decade roll off. Does everyone see this? If it were 20 dB per decade, it will just be A0 by K into, okay, for that all of this, this is 1, sorry, that is 1. Okay. So what is this? What is square root of A0 by K roughly? 30, right? So this is 30 times omega 1. Okay. Now how will the phase plot look? What's the final value of the phase? Minus, careful, it's a second order system, it should be minus 180 degrees, minus 90 here, okay, minus 45 and minus 135. Okay, so what will be the phase at this particular value? Minus 90. Okay, and then close to this, will it ever hit 180? Why? Why will it never hit 180? Because it's asymptotic, right? It's a tan inverse function. So it will never actually, it's a second order system, so you will never really hit 180, but you will be close to 180. Right? Something like that, right? All right. Now, okay, good. With the compensation, how will it look? This is 10 power 6, and I am going to, and what is my compensated value of omega 1? This is, sorry, just by putting that C alpha, I am not compensating it with, I am not doing Miller compensation yet, just with C alpha. What happened to my P2? P2 remains here, right? This is omega 2 equal to this is omega 2 equal to omega 1, right? Both are identical for the case without the C alpha. Okay, with C alpha what happens? Right, it should go to the left, and where will that be? Right, it will almost be here, right? It will almost be at this point itself, and it should fall at minus 20 dB per decade. And where should it cut this axis? To the right or to the left? Be careful. Where should it cut? No. Right, left. Okay, go back and see. You have your omega 1 here, right? Your omega 2 has, your P2 we discussed was 4 times your new unity loop gain frequency. So if this is here, it should cut to the left, right? Okay. So just think a little bit. So I am just drawing it like a little stub there, and then I drop like that, something like this, right, up to here, and then it should go at minus 40. Okay. So this would be minus 20 dB per decade. This value will be your new omega 1 prime, right? This is also your omega 2 prime. Omega 2 prime is omega 2. We have not, sorry. Okay, the way I have written it is all confusing. This 10 power 6 is your, this is omega 1 equal to omega 2 equal to omega 2 prime, and this is omega 1 prime, and this is your omega u prime loop, and this is your omega u loop. Okay, prime is after including the C alpha. Okay, all right. So do you see that at least it seems to work better, right? Because your, what's now the phase margin? The new phase margin is fairly low, right? So you are okay. Actually, the way I have drawn it may not be very correct, right? This was just drawn by hand, so you might actually have something. Okay, something like that. That is minus 90. So it will be somewhere here, right? Okay. Am I right? Go and check this. I think it should be okay. Phase plot I am a little wary, but I think it should be okay. Okay. Anyway, go and check this. Basic ideas are this. All right. So the essence is here that you need a very, very fat C1, sorry, a very fat C alpha, right? Very high value of C alpha in order to do this. Okay. Now, what did we know we can do? We can also do the Miller compensation. So, what I will do is actually send you a PDF. It's a very nice tutorial article from MIT which discusses some of these aspects. Just go through that, okay. But we are covering pretty much everything, but it puts it in another way, all right. So, what did I say? Here I am going to add my CC this way, all right. Now, how do you calculate what is the transfer function for this? Okay, does this look like something familiar? What? Frequency analysis of what did we see a circuit like this? Common source. Very good. Good. Okay. So, how did that look for the common source amplifier? Right. Go back and see what you had. Let me draw it here. You had a plus minus Vi, right? Then you had some Rs. Then there was a capacitor. What was this capacitor? Gs. Okay. Then you had everything going this way. I had a Gm times what? Let me call this as some Vs. It was Gm times Vs. No, that is not Vs. Call that as Vg. Gm times Vg. Okay, that is actually Vgs. So, Gm times Vgs. Then there was some resistor. What was that resistor? Some RDS or R naught or whatever. And then you had a capacitor. What was the value of that capacitor? CdB or something. But anyway, some CdB we had there. Okay. The details are not important. What was this whole thing is for the common source amplifier. And there was a capacitor here. What was this capacitor? CGD. We have already analyzed this particular circuit, and can you map these two things together and tell me what are the values of the two poles? Okay. This particular system, did it have poles only or did it have zeros also? Okay. How did you calculate the value of the zero? Did it have a right half plane 0 or left half plane 0? Right or left? Go and check. It had a right half plane 0, right? And had left half plane poles. And how did you calculate it? Yes, but you remember the explanation I gave you for when do you have a 0? When do you have a 0? More than one path, right? You remember the interference example that we gave for more than one for more than one path. So where are the two paths? This is one path and that is one path, right? So the 0 came at what? Your omega z was at Gm by CGD, right? So let me say this is an aside on common source amplifier. Okay, you had 1 0 at this. Then what was the two poles? Omega P1 and omega P2. This was a right half plane 0. Your poles are both on the left half plane, right? And these are the magnitudes of the poles. What was the first pole? Approximately, at least? It was 1 by RS, and then you had CGS and so we can simplify that. So you had CGS plus the gain. What was the gain? Gain was Gm times R naught times CGD, correct? And this we can approximate as 1 by RS into of these things, which is the largest value? This one. So I can write this as R naught Gm CGD. Okay. Now, if you compare these two things, right, where do you expect your solution to appear now for the circuit that we have? How do we compare first? You can make a Norton equivalent of that guy, right? And what will the Norton equivalent of that guy be? What will the Norton equivalent look like? Plus minus, and then you will have the same R3 here, right? And what will be the value of this guy? Remember that you will have a minus GM1 what? R3 into Vd, correct? So that is the Norton equivalent. Well, yeah, this is the Thevenin, that is the Norton. Okay, this is the Thevenin equivalent. The Thevenin equivalent of everything that is in orange, in yellow. Okay, so what will this thing become in our circuit? 1 by G M what? 1 by G M, careful. All of this GM1 should not appear at all, it should only be this one, right? This is the amplifier that you are, so it should be GM5. Okay, what is your RS? R3. What is R0? R6. And what is CGD? CC. Okay, and what about this omega P2? Yeah, so that one even I forget, and it turns out that the approximation that we did over there was not particularly the best approximation. So go back and read the PDF that I have sent you. Okay, this is a slightly different approximation, but this also works. Okay, and you can, I'll write it here directly, and then you can go and see what the equivalent thing should be for the common source amplifier. Okay, so this is something that I have. Go and check that this is correct. GM5 times CC into C1 C2 plus CC into C1 plus C2. Okay, I think when we did the analysis, we had not taken something into account, and so, right, I think what had happened, C1 CC plus C1 C2, I think we had not taken the C2 CC into account, but it's okay. All right, you can go and look at that PDF, and it tells you how to derive this. So I'm not going to write down the corresponding expression here, but the idea is that you can find out the two pole positions based on an analysis of the common source amplifier and mapping that common source amplifier to the circuit that we have. Okay, just the component things have to change, so you don't need to do the whole calculation again. Okay, now remember you have the 0 here, right, and we'll talk about the 0 later. Again, I'm not going to deal with that 0 completely because that's a more involved thing, but I'll just tell you what happens. You will have a 0 in the final result. Okay, so we'll come to that later. Okay, yeah, that's all I've done. That's all I've done. For 0 also, correct. 0 will be that. Yeah, 0 will be that. 0 will be identically that, right? 0 will be what? The 0 will be at, the 0 will come at this omega z would be at what? GM5 divided by CC. This will be omega P1 and this will be omega P2. Okay, the important thing is, by putting a CC here, what happens to P1? So omega P1 has shifted to the left, omega P2 has moved to the right. So you will see an advantage, right? In the previous case, when you put just a C alpha here, you are not troubling P2, you are only making P1 come to the left. And so there are two reasons why you need a very high value of C alpha. One is that you want to ensure that P2 is 4 times the unity loop gain frequency, and P2 is not moving. So P1 has to move, it has to move enough to ensure this. Second thing is that because you want a very low value of P1 and you are not using the Miller gain, you have to have a very high value of the C alpha. Okay, so the moment you have this kind of Miller compensation, you see what we have already discussed, and that is called pole splitting, right? Miller compensation implies you have pole splitting. And what does pole splitting mean? Pole splitting basically is that your omega, so I will call these as the primed values. The pole splitting means that omega p1 prime is greater than, sorry, this is less than omega p1 and your omega p2 prime is much greater than omega p2. Okay. Now, all of these p1, p2 and everything is referred to this circuit, not to the common source amplifier, right. This is for common source, right. This p1, p2 I am using it interchangeably, but from context please be aware what I am doing. Okay. All right. So, now what can you do? You can go and find out as homework, please go and find out what is the value of Cc now. What is the value of Cc that ensures damping factor zeta is equal to 1, implies your P2 prime is equal to 4 times the unity loop gain frequency A naught by K into P1. Alright. Alright. So, I will leave this page empty. Please finish this and come. This is like your tutorial. We are not giving an explicit tutorial for this topic, but given that I have spent so much time on this, you can expect some stuff on this later on. Alright. Now, let us go back to something very, very important. We know now how to calculate your Cc. Okay, just as a guess, can you tell me whether Cc that you calculate here will be greater than or less than C alpha? Significantly less? Yes. That is what we want, right. Your final answer should be in the picofarad range. So, go and calculate it, you will get a quadratic, just go and calculate and see what value of Cc you get. Okay. Tell me this tomorrow. Alright. Now, let us consider these two cases and you can tell me something interesting about it. Okay. Let me take an amplifier like this. Let this have a function A of s plus minus, okay, and let me again as usual I have a feedback network which I have connected like this, right. How did I connect the feedback network? Right, and this was k minus 1 times r and this was r. Okay. So, we mapped this actually to something like this, right, having an A of s and then you have a return path which was B, and we said B is frequency independent and we put it like this. Okay. Can you tell me what is the value of B? We found that B is 1 by K. Okay. And what is the value of the closed loop gain in the case of at least DC value of the closed loop gain? If your A naught, if A of s is very high and all of that, ideally ideal closed loop gain is nothing but what? A0 is infinity and all of that. Then what will it come to? It will just be K. Okay. So, right, and your K is going to be greater than equal to 1, right. You want an amplifier. So, you finally want K to be greater than equal to 1, alright, which means your B is less than equal to 1. Okay. Now, go back to what we discussed earlier, right. Is the closed loop amplifier more likely to be stable for high or low values of A naught by K? Was it the high value that troubled you or the low value that troubled you of A naught by K? Think again, right. We discussed this. We took a third order system, right. We said that A naught by K cannot be more than 8. Then we did the dominant pole frequency compensation in the quiz and we found that A naught by K has gone to 900, 890 or whatever, right. So, there is, it is more likely to be stable for low values of A naught by K, which means given a value of A naught, right? If I increase or decrease k, will it become less stable? Be careful. Increase or decrease k? Careful. If I, okay, I am going to fill this k, the amplifier becomes less stable. Okay, this less stable and more likely and all are just very colloquial usages, but you get the idea, right? What should I fill here? Decrease. Is that right? All right. So what is the hardest value of k for stability? K equal to, k I said is greater than or equal to 1, right? Implies if my closed loop amplifier is stable for k is equal to 1, implies the amplifier will be stable for all k greater than 1. Correct? Just a corollary of what we have done. And so when you buy a commercial op amp, right, like your 741 or what were the other op amps that you are using, who has used OP07? We bought some OP07s because you people needed it. Okay, how many of you are using the op amps in your exercise? Only 1, 2. Which op amp are you using? 741. What are you using? Okay, some other op amp. Okay, all right. So when you buy an op amp, the manufacturer does not know what is the value of k that you are going to put, right? You may want to have a non-inverting amplifier of gain 10, gain 100, gain 1000, whatever, right? But he does not know that. So what is the value for which they can compensate your circuit? 1, right? And so all commercial op amps are unity gain compensated, which means what? They are guaranteed to be stable when you have a feedback of 1, right? And so you can use it for any value of feedback which is more than 1 and it will still be stable, it will not oscillate. Okay. Now given that kind of op amp, if you want to make it oscillate, what do? Increase? No, you have to decrease k, which means if you put another amplifier in its feedback path, right, and increase the value of B, which means you are decreasing k, you can make any op amp oscillate. Okay, and we will do this in the lab next semester. Okay, you will take one op amp, you take another op amp in its feedback path, keep increase the gain of the second op amp, and you will see that the first one begins to oscillate. Okay, all right. Now there was the small thing about the 0, right? I forgot to mention that. Okay, we just finish the 0 thing and then so what did I say? I said that if I put a capacitor here, right, it introduces a 0 and the value of the 0 is at what? GM 5 by Cc. Okay, so there is a trick and I want you guys to go and calculate it and see for yourself that it works. And the trick is that I believe if you, even I have not calculated this, so that is why I did not want to teach it here, but you can go calculate it, it is a little messy. If I put some value of R here, okay, let me call that as RC and then I put a Cc, all right. You take this combination and you will see that you can actually choose RC to kill the 0. Okay. So this is another homework for you. It's a little involved, but it will be interesting if some of you can do this. Okay. Just calculate what the transfer function, what the 0 of this transfer function will be, and then just allowing an RC to be here will allow you to actually kill that 0. Okay. So, the 0 can be taken care of. So, anyway, just go and look at that. Okay. All right. Now, let us go back to the op amp. So, we had an op amp whose transfer function A of S was of this form, right, sum A naught divided by 1 plus S by P1 into 1 by S by P2, correct. And we already saw that because the op amp has to be unity gain compensated, right. Did I write unity gain? Yeah, unity gain compensated. What do you know about P1 and P2? Is it reasonable to say P1 is much less than P2? This is reasonable to say. Okay. And okay. So, how will this transfer function actually look? How will this transfer function look? We drew it, right. So, it will be P1 till some small value, then minus 20 dB per decade, and then minus 40 dB per decade. Okay. And what will P1 and P2 be? This will be P1. Okay, I am using P1 and omega P1 interchangeably, be careful, it is all the same stuff. Okay. P1 is the pole, it may have a negative sign, but I am taking the magnitude, so be careful. Okay, let me call that omega P1, and this would be omega P2, correct? Right, I am wrong. Should not be like this. How will it be? That was what I wanted to show actually. It crosses like that, and then you have your P2, right. So, this is your omega P2. All right. Now, what is this quantity? Let me say this is just A of S, and we just discussed that your worst case operation is when k is equal to 1. Okay. So, if k is equal to 1, what can you tell me about open loop gain and the loop gain? Same, right. So, k equal to 1 implies your A of S is identical to your L of S, right. This is your open loop and this is your loop gain. All right. And from our discussion about feedback, right, which frequency range in this plot does feedback appear in the closed loop? Less than what? What is this frequency? This is the omega u loop. So, we said that feedback actually operates only when the loop gain is greater than 1, right. So, that is in this region. So, this green region is your frequency range of interest. Beyond that, there is no feedback, right. That means you will only get the open loop function. So, you are going to actually operate only in this region. So, can you now approximate your op amp in this region? Approximate transfer function of op amp in the useful region of frequency. What will it be? It will be A naught divided by, what do you see over here? Does P2 trouble you at all? No. So, you just forget about P2. So, it will just be 1 by S by P1. Okay. So, this approximately looks like a first order system. Okay. So, for a first order system, what do you know about gain and bandwidth? Gain bandwidth product for a first order system is constant, right. So, remember this point in mind. Tomorrow what we will see is we will take some simple amplifiers right. We will take for example the inverting amplifier, the non-inverting amplifier and the source follower, right, or the buffer, and we will see which of these actually will give you the highest bandwidth for the same gain. Okay. All of that follows from this, and that is why it is very important for one to understand how the op amp functions, how it is compensated, and what are the implications of these two in actual circuit design. Okay. We will do that tomorrow, and we will start with BJTs tomorrow. Thank you.